Alright guys, in the last lecture we really introduced matrices and some operations we can do on them. So we looked at how to add two matrices if they were the same size and how to scale them if they were being multiplied by some scalar constant. So let's start off this lecture by reviewing a question that could have been taught in the last one. So here we go. We're given two matrices, A and B, and our goal here is to find what 2A plus 5B is equal to. So if A is represented by this matrix, then 2A is all of these entries multiplied by 2. So that means 1 turns into 2, 4 turns into 8, 2 turns into 4, and so on and so forth. Similarly, if B is represented by this matrix, then this matrix right here, then 5B would just be each element inside this matrix being multiplied by 5. So luckily for us, most of them are 0. So all of the diagonals, still go to 0, but these crosses go to 5, right? Okay, now the last thing we have to do is add these two matrices together. We have to add 2A and we have to add 5B. So whenever we're adding matrices, just add the corresponding entries. So top left adds with the top left. So I'll have 2 in my new matrix in the top left. In my new matrix in the top left, my value will be 2. I'm going to add top middle plus top middle. 8 plus 5 is 13. So in my new matrix, my resulting matrix, the top middle value will be 13. And so on and so forth. So you'll get an answer that looks like this. So hopefully this should be a review. If you're still a little confused on it, rewatch the last video and it'll all make more sense to us. Okay, so we know how to add, we know how to subtract, and we know how to multiply by a scalar constant. But what we don't know how to do is we don't know how to multiply two matrices together. So what happens when we multiply A times B? So before we go into actually doing it, let's start looking at a question. Okay, let me zoom out just a hair. Just a hair. Okay. A certain store sells apples, pears, bananas, and strawberries. And the apples are priced at $1, the pears are priced at $2, the bananas at $3, and the strawberries at $4. On the first day, the store sold 8 apples, 10 pears, 3 bananas, and 6 strawberries. On the second day, it sold 2 apples, 4 pears, 12 bananas, and 9 strawberries. The question is, what is the total profit? Now, this seems like a very arbitrary question, but it's okay. This is how we build more complicated structures in math, right? We start small and then work big. So an easy way to compute this is this. Make a little t-chart, right? So in my rows, I have each fruit and what they're all priced at. And in my columns, I have how much were sold in each individual day. So for instance, well, I think you know how to read a chart. So on day 1, we sold 8 apples, each priced at $1. On day 2, we sold 2 apples, each priced for $1, and so on and so forth, right? We got day 1, we have 3 bananas priced at $3. Those are expensive bananas, by the way, and so on and so forth. So if you take all these numbers and you add them together, you will get your total profit. Well, at least your total revenue, right? Maybe the question should have been, what is the total revenue? So if I add all of these if I add this entire column together, I'll get my total revenue. I know they said profit, but let's just call it revenue. Okay, easy enough. You guys could have done that in your sleep. But the thing about this is I want you to think about this yellow column that I kind of ignored at first. It says using the distributive property, notice how 1 times 8 plus 1 times 2, I can rewrite it as 1 times 8 plus 2, right? I could factor out that 1. Same thing with the pairs, like 2 times 10 plus 2 times 4 equals 2, factor out a 2, and I can add 10 plus 4, which is 14. So I can do that with each one of these guys, with the apples, the pears, the bananas, and the strawberries. I can write them in a form where I'm kind of using this distributive law. And everything in parentheses, so like this 1, this 2, this 3, and this 4 represent the price, and everything in the brackets represent the total amount sold across the 2 days. So that's kind of, matrices are annoying in the sense that they don't take the normal approach to this question that we would. They use like kind of like the distributive rule. So they use the distributive approach as a mindset for matrix notation, where in our case, the way I set up the question is that matrix A is the price of the fruit, and matrix B is the amount sold each day. So you'll see what I mean. So here's matrix A that I created. Matrix A is what we call a row vector. A row vector is a matrix with only one row. And remember, each row of a matrix and each column of a matrix has to have some sort of uniting quality. So what is the uniting quality of the row here? Well, if I look across, these are all prices of the fruit, right? All these guys are just prices of the fruit. And each individual column, well, they're a different fruit. The first one represents apples, the second one represents pears, the third one represents bananas, so on and so forth. So this is how I'm going to set up matrix A. Matrix B, like I told you guys, is going to be the amount sold each day. So matrix B looks like this, where column 1 represents the day that we're talking about, and column 2 represents the second day, and each row is going to talk about or represent which fruit we're talking about. So for instance, this 10, what does this 10 represent? Well, it says that on day 1, I sold 10 pears. Hopefully that makes sense. Oh no, I lost my arrow. It's okay. Oh, there it is. He's back. Okay, so similarly, what does this 12 represent? It says that on day 2, I sold 12 bananas, right? So what I'm going to look to do here is I'm going to take matrix A, which is a row vector. Oh, by the way, a row vector is a matrix with only one row, and a column vector is a matrix with only one column. But that's not really that important, but it might pop up here and there in your notes and in your homework. Okay, anyway, what I'm going to do is I'm going to take matrix A and matrix B, and I'm going to multiply them. I'm going to multiply them together to try to find my total revenue. So now the question is, how do I go about computing matrix multiplication? This is what our process will be. We're going to multiply each individual row of my first matrix to each individual column of my second matrix. So I'm going to take all the rows in matrix A, and I'm going to multiply it to all the columns in matrix B. So we're going to have to do this one by one. So what's going to happen is you're going to constantly get a row vector multiplied by a column vector. So it's going to look like this. So this, anytime you have a row vector and a column vector being multiplied by each other, we call this the dot product. Again, this is not very necessary to know these names, but for your test, you're just going to have to know the process. But it's good to know if you go on to like physics and stuff like that. So what we're doing is we're calculating the dot product of all these vectors. And right here, what I did is I took the first row of the first matrix, and I'm multiplying it by the first column of the second matrix. Okay, so what is going on here? When I perform the dot product, what's going to happen is I'm going to multiply each corresponding term. So look, I'm going to multiply the first two terms, then I'm going to multiply the first two terms to get this, then I'm going to multiply the second two terms together to get this, then I'm going to multiply the third two terms together, then I'm going to multiply the last two terms together. And once I do that, I add them all up, and this is my value. This is my product, my scalar value after I perform the dot product. Okay, so remember how you go about computing the dot product. You take each corresponding value, so 1 and 1, multiply them together, 2 and 2, multiply them together, 3 and 3, multiply them together, and the fourth and fourth, multiply them together. Then add them all up. Take a second, glance at it, understand, and let's do the next one. So remember, we had to multiply all of the rows of the first matrix by all of the columns of the second matrix. Well, we got lucky here because matrix A only has one row, so we only have to do this 2 times. So now what I'm going to do is I'm going to take the first row of matrix A and multiply it by the second column of matrix B. Again, we have 2 vectors being multiplied, and I'm going to perform the dot product on it. So I take the first 2, multiply them together, take the second 2, multiply them together, the third, multiply them together, and the last, multiply them together, and then I'll find their sum. And this is how we compute the dot product. So the first one, we got 61. The second one, we got 82. And you'll see how what we're going to do with those in a hot second. But before that, we talk about, we spoke about size and dimension in the last lecture. So this is good. So finding the resulting matrix. So the dimension of the resulting matrix has the same number of rows as matrix A, and the same number of columns as matrix B. So for example, if I have A times B, and A has dimensions 3 by 2, and B has dimension 2 by 4, then the resulting matrix will take the row of this guy and the column of this guy. So A times B will result in some matrix C that has dimensions 3 by 4. Okay, so let's look at another example. If I have matrix A that's 5 by 6 and matrix B which is 6 by 7, then after we do matrix multiplication, the result will be a matrix of 5. Oh geez, I meant to use a highlighter there. 5 by 7. So take the row of the first one and the column of the second one. Lastly, if we have A times B again, maybe I should change these letters up, it's okay. Then the resulting matrix would be the row of the first one and the column of the last one. So our resulting matrix will be of dimension 8 by 1. So for us, we have this guy, which has 1 row and 4 columns, right? A has 1 row and 4 columns, and B has, that's a B, I swear. Okay, that just made it look worse. Let's fix that, okay? And B is 4 rows and 2 columns. That means the resulting one will be 1 by 2. That means the resulting matrix will have dimension 1 by 2. Now, one thing you want to notice here is, if we go back to these previous examples, is we were looking at the outside, meaning 3 and 4, 5 and 7, 8 and 1. We're looking at the outermost numbers to find the dimension of this guy. But did you guys notice something special about the inside of the inside values? Well, this guy's column is 2 and this guy's row is 2. This guy's column is 6, this guy's row is 6, this guy's column is 8, and this guy's row is 8. Even here, this guy's column is 4 and this guy's row is 4. So all of them, the closer numbers, they're all matched. So actually, this is a rule of matrix multiplication. If you're multiplying two matrices, these two inner values have to match. If those two insides don't match, then you cannot perform matrix multiplication with whatever two matrices you're trying to multiply. So always make sure before you start multiplying matrices, make sure that the column of the first matrix is has the same value as the row of the second matrix. Okay. So moving on, we found out that our resulting matrix will have 1 row and 2 columns. So our matrix will look like this. It has 1 row and it'll have 2 columns. Now the question is, what are my entries? Well, my entries are the result of my dot product, 61 and 82. But which one goes in which question mark, right? There are 2 spots and there are 2 results. So which one goes where? Well, here's how you know. See, this 61 came from the first row and the first column. So guess where this guy's going to go in our resulting matrix? Yep, it's going to go in the first row and the first column. Just like this 82, we found it by crossing the first row and the second column. So guess where this 82 is going to go? It's going to go in the first row in the second column. See how it all comes together? Isn't math beautiful? It's awesome, right? Okay, so let me scoot over. Okay, 61 was found by taking the first row and the first column. 82 was found by taking the first row and the second column. So that means we're going to put 61 in the first row, first column, and we're going to take 82 and we're going to put it in the first row, second column. So it's going to look like this. And remember, this is reflective. This notation that I'm showing you guys right here, is reflective of what we said in the last lecture, where how we spoke about the elements of matrices, right? So this guy would be little c of ij. If you go back to the last lecture, I wrote that in the notes. Okay, so this is our resulting matrix after we perform matrix multiplication. So what does this tell us? If you take the sum of these two numbers, you'll get the product, the profit, or in actuality, the revenue. So 61 plus 82 is equal to 184, and that is our revenue. So it was a word problem, but the main point was to start talking about the steps in matrix multiplication. And we took something that was so simple and wrote it in math notation, made it so complicated and long-winded when it really didn't have to be. But it was for the purpose of introducing matrix multiplication. We're going to do 2 more examples in the next lecture, so I'll see you there.